jump game number 6. So we are giving a 0-indexed array nums and an integer k, and we are initially starting at index I equal to 0. In one move, we can jump at most k steps, so k equals to 2 for this example. So from here, we can jump 2 steps, without going outside of the boundary of the array. So that is, you can jump from index I to any index in the range. So we can jump from a range I plus 1 to the minimum of the range n minus 1 to I plus k inclusive. So we want to reach the last index of the array. It means index n minus 1. So our score is the sum of all nums j for each index j you weighted in the array. So we can jump like this. So for the first step, we're going to be at this position, index 0, it is 1. Now we are going to jump to the second index because this is going to be optimized. If we jump, we're gonna because normally we can jump to -2, but that is not the optimum solution. So we're gonna jump 1 step. We're gonna jump to -1, and then we're gonna jump 2 steps because maximum we can jump 2 steps, and then we're gonna jump 2 steps. So the result is gonna be 1 plus -1, 0, 4 plus 3, it's gonna be 7. So this is gonna be our final result. I think the basic idea is that we can solve it by using dynamic programming, maybe. But let's just try to use DFS with memorization to check if we can solve it by using DFS with memorization. So we're gonna start in from the index I, and I will give a pass, and now I'm gonna return the DFS. So I'm gonna start in from the 0 index. So I must reach the last index. It means n minus 1. So I have to check it for the n minus 1. If I equal to n minus 1, I'm gonna return the value. It's gonna be nums n minus 1, right? So this is our boundary check. Now we're gonna have a result equal to 0, and we're gonna check the maximum value in a range. So for z in range I plus 1, so according to the formula, and the minimum of, let's just copy it. So I plus 1 to minimum of n minus 1 to I plus k. As it is Python, we're gonna plus a 1 outside. So if it is inside the range, we're gonna check the maximum value. So the result is gonna be the maximum with the result with DFS j, and plus my I is going to be nums I, and this is going to be the initial solution. We are not sure if we can solve it, but let's just try. I did something wrong. DFS J. There's a non-type. Let me just check what is wrong with it. It's going to be the maximum of this result. With dfj plus nums I, unsupported operation for plus and num. I must did something wrong. It means I get a non-type. Let me put it in this way. So minimum is gonna be n, and this one gonna be I plus k plus 1. I think this is gonna be right. Let me just run it. It's the same. So it's gonna be the maximum of the result with dfj plus nums I. I must did something wrong. Unsupported operand types for plus, non-type, and integer. Yeah, because I didn't have a return, I think. I forgot about the return. Now let me think. So the DFS is gonna have a return and it's gonna have a number, so it will not have the none type. Yeah, now let me just run it. It seems okay, but for the last one it is not right. Yeah, as you can see, it should be 0, but I return a 3. It means my definition is wrong, because this result should be negative infinity. Yeah, because there's negative values, so the result can be negative. So I cannot set a result to be 0. It has to be a negative value. Now let me run it to check. Yeah, now it seems okay, but let's just submit it to check if we can pass. Yeah, it seems we cannot pass because this is n times k times complexity. N is 10 to the power of 5 and k is also 10 to the power of 5. As you can see, there's a range, and this is OK and this is On. So the time complexity would be On times k. Yeah, so this means we cannot pass using this kind of a solution. Basically, we can, yeah, as you can see, we cannot pass. We passed to 57 testing cases. Now we're going to optimize this kind of a solution. So why not we can use tabulation to optimize it? Yeah, maybe from here, definitely we didn't get the right solution, but this is difficult to check what is wrong with it, because it's difficult to optimize from n times k to n log n or On time. This is difficult to check. So why not we just optimize it to a tabulation? Maybe it's going to be easier for us to find the problem. So we're going to prepare a tabulation to solve it. So it's going to be 0 times n, and f0 for the first position, it's going to be nums 0, so it should be okay. Yeah, we just turn it into a tabulation problem. So for I in range from 1 to n, and we can check the fi. Yeah. So fi would be the maximum of the previous value plus our value. It is nums I. Yeah. And finally, we're gonna return f minus 1. So the maximum value is just a range. So it is f minimum. Yeah, let me check maximum from 0 to I minus k. Yeah, to I. So this is gonna be our range. Let me just give you an example. Maybe we have 1 minus 1 and minus 2. Yeah, maybe I'm gonna use another example. Maybe we have 1, 2, and 3, and k also equals to 2. Yeah. So we are going to check this position. For example, the value here for this 3, and this is our f. So we want to check previous value plus nums I. So for example, this is nums I is 3, and we're gonna nums I, let's just say nums I equal to 3. We just want to check the previous value for the dynamic programming part for the f. Yeah, so we're gonna check 0 to I is 2, 2 minus k is 2, it is 0. Yeah, so it means this is the maximum of them 0 to 2. So 0 to 2, it is 1 and 2. We're gonna choose a maximum value. It's gonna be 2 plus 3. So this is gonna be our final result. And this is nums, and this is f. Yeah. Now let me try to run it to check if it is okay. As you can see, it is okay. Now let me submit it to check how many testing cases we can pass. Yeah, and the time complexity gonna still be n times k, and normally we cannot pass because this is not okay. But now it seems the problem is clear. The problem coming from this max function. Yeah, it's also past 57 testing cases, but we cannot pass. It seems we need to optimize the maximum for this f. Inside the f, there's gonna be a maximum from 0 to I. Maximum of 0, I minus k to I. Yeah. So it means inside a window, and this is a fixed window, and the window size is k, and we want to get the maximum number inside this window. Normally it is a monotonic queue. We can solve it. Monotonic decreasing queue, we can get the maximum number, and this is gonna be O(n) time. Another one is we can use a sorted list in Python. So it is basically the balanced binary search tree. We can solve it in n log n time. So why not let's just try n log n time first. So we're gonna use a sorted list. So from the sorted containers, we can import the sorted list. Because inside the sorted list, we can check the maximum element inside a window. So from here, we're gonna prepare a sorted list as L should be equal to the sorted list, and we're gonna prepare L index at the left side. It's gonna be 0. So for this one, this is basically used to check the window size. If the window is too big, normally we're gonna remove some element. Yeah. Now, for here, we don't need to use this one. We want to optimize to a sorted list solution. So we're gonna use the sorted list. We're gonna check the maximum element inside a window. So it's gonna be SL minus 1, because this is gonna be the maximum element. So we're gonna put the first element inside the sorted list. So it's gonna be nums 0, because this is gonna be the first element. And then for the second element, for I in range 1, so for I in range 1, we're gonna check the f function. So f is still the dynamic programming part, but we're gonna use the sorted list as well. So for each of the index I, so the sorted list gonna add an element. This is gonna be log n time. So it's gonna be nums I, and then if this sorted list, the length of the sorted list is more than k, it means it is too big. So we're gonna remove an element from the sorted list. So sl.remove, we're gonna remove the let me check which element. So the element is let me check which element we're gonna remove the element at the left side of the window. Yeah, so it's gonna be FL. So this is gonna be the element we needed to remove, and here it is not nums, because we've already turned our problem to, let me check. So for here I get a fi, and I need to put this fi inside my sorted list. Yeah, I believe so. So I'm gonna put the fi inside my sorted list and then remove the fl. Because for my sorted list, basically I'm checking the function, the dynamic programming function, f. Yeah, let me just check. So for here, I get the final result, and for the sorted list, I need to add this element. Yes, it is. Because before that, I'm checking also about the f function, the dynamic programming part. This means here I have an element, and here is a sliding window, and inside this window is my f function. Yeah, and this is my fi, and this is some element before it, and it's gonna be maybe I minus k to I. Yeah, I'm going to check these areas. So this means for my sorted list, I need to add my element fi, and if it is more than k, it means the window size is too big. I'm gonna remove from the left side, so my index is L. After remove that, the index from the left side L should plus equal to 1. And finally, I just needed to return the last element inside my dynamic programming array, so f minus 1. Now let me run it to check. As you can see, it works. Now let me submit it to check if we can improve a little bit. Yeah, I think it's gonna take some time, but let's just have a check if it works. Yeah, as you can see, it works. Actually, it is less than 1 second, but it is okay. But as you can see, it is just 5% of all Python submissions. It means it is not the best. Yeah, because this is a log n time solution. As you can see here, this is ON for the dynamic programming part, F array. And for here, basically inside the SL, we're gonna add and remove element. So this is n times the log k. So the time complexity up to now, it is n times log k. And this log k is the window size. Basically, it is also 10 to the power of 5 for this k. Yeah, because for here is for checking the window size, and the window size is k. Yeah, but at least it can pass. Now we want to optimize the sorted list to monotonic and decreasing queue. Yeah, because basically if we want to calculate maximum element in a fixed window, basically we can use a monotonic queue to solve it in ON time. Yeah, so now we're gonna delete the sorted list because we will not use it. Yeah, I'm gonna delete these areas. I don't need the sorted list part. Now I'm going to use a monotonic queue to solve it. So I'm gonna prepare a queue. It's gonna be the queue. Inside, I'm gonna put the first index 0 as well. So I put the index inside. Now let me delete these areas. Yeah, but let me just go back to the dynamic programming part. Maybe this is easier to find. How can we solve it by using monotonic queue? Yeah. Now let's go back. So here is the dynamic programming part. Basically, we're gonna optimize this formula. Yeah. So we're gonna prepare a queue. Queue gonna be the queue. Inside it, I'm gonna put the first index 0. Now from here, so fi should be equal to what? Because we are preparing a monotonic decreasing queue, it's gonna be q 0, because q0 is gonna be the maximum element. Yeah. Now let's just try to write the monotonic queue first. So while q and my current element is fi. So fi is more than fq minus 1. So I would to pop it out. So q dot pop left, and after that, the q can embed the index I. Yeah. Now we want to check the window size, because the window size is k. We have to check that. But how can we check that? We're gonna use if check. Yeah, because definitely we don't need to check the queue. There's gonna be something inside the queue. At least it's gonna have index 0 inside the queue. So we don't need to check the queue, because the window size k is always more than 1. It means there is always something inside the queue. Basically, we just need to pop it out. So we don't need to use while. We can use if check because the window size is fixed. Yeah. Now we want to check the window size. So this window size can be checked by I minus q 0. So if it is more than k, so it means the window size is too big. So for example, the I is 0, this is I, and I is 2. Yeah, let me use so for example, I is pointed to index 2, and another one is q0. Maybe q0 is at 0. So this is a q0. It is at 0, and the k is also 2. Yeah. So normally the I minus q should be less than and equal to k. But if I equal to 3, it means the window size is too big, because 3 minus 0 is more than k, more than 2. So it means I need to pop it out. Yeah. So from here, q needed to pop out from the left side. Yeah. here I did something wrong, because here is basically monotonic queue, and from here I need to pop from the right side. I just need to queue.pop. Yeah. Now let me check if I finished everything about it. Normally the queue should always valid. There's some element inside the queue, so I need to check the window. First of all, I'm gonna keep the window size. Yeah, but from the beginning, first of all, I'm gonna check the window size. If the window size is okay, basically there's something inside the queue, and my function gonna be q0 plus nums I. It's gonna be the same, and then I'm gonna use the monotonic decreasing queue to check it. Yeah. Now let me run it to check if it works. It is not working. Not working. Yeah, so for this one it is not working. Let me just check what is wrong with it. So I need to put, yeah, basically this is my queue for I in range. So if I minus q0 more than k, it means more than the window size. I need to pop it out. So q should pop left, it means the first element, and then I can check my result. Yeah, I think it should be okay. Fi should be q0 plus nums I. So while q and fi more than so currently this is fi, this is fq minus 1. So q need to pop and append the value. This is not q0, because q0 is just index. Actually, I need to have the value. It's gonna be fq0. Yeah. Now let me check if there's something wrong. Yeah, let me just run it. Yeah, now it seems okay, because I just forget about it. This is just the index. I need to take the value, so it's gonna be fq0, and it's gonna be the value for our formula. Yeah, and then we're gonna plus the nums I. Now let me submit it to check. Yeah, now it seems okay, but you can see the speed it is much faster, because currently the time complexity is O(n), and also the space complexity is O(n). Yeah, this is the final optimization for the problem. I think this is going to be the best solution for it. Of course, you can also optimize maybe the space, but basically I think this is okay for the problem. Thank you. Yeah, that's just yeah, thank you for watching. See you next time.